that I have with you today and tomorrow. And so I'll basically just set a backdrop of topics. If you're interested in something, if you have questions, please interrupt me and ask, and then we'll dive a little bit deeper into those topics, okay? How many of you are from an applied math background? How many from a physics background? Okay, how many engineers in the audience? There's my engineers. Okay, what are the other fields? I'm just curious. Pure math, okay. Oh wow, applied math, pure math, good. How many pure math? Oh wow, okay, it didn't even occur to me. Yes, good, pure math. Who else? I'm sorry? Okay, astronomy, good. You guys?
Too young, I'd say.
Okay, finding yourself, good. Finding your applied maths, okay, good. All right, so how many of you have done some Koopman operator theory applied in the past? How many of you are learning kind of for the first time? Okay, perfect, good. So I'm going to start with, of course, x dot equals f of x. This is our basic dynamical system. This is our entry point to the natural world. So all of the world around us, essentially, is complex, multi-scale, high-dimensional, and nonlinear. And we model it with differential equations that describe how our world varies in space and in time, okay? I'm a mechanical engineer, so I like dynamics. I like things that move. My friends in civil engineering sometimes get rid of the x dot. It's a little simpler, but most of us have time-varying systems. And the challenge is, this is not a comprehensive list that we experience in data-driven dynamics. Often our equations are unknown for systems of interest. For the systems we actually care about, like the brain. We're in a world now where we can actually measure thousands of neurons simultaneously in time-resolved experiments. We have no equation for the brain like we have for fluid dynamics, okay? Epidemiology, we don't have an equation for how COVID spreads across a continent. Many other systems we would like to understand, we don't have the equations. And so I think the fundamental point here is that equation discovery, discovering dynamics purely from data, enables two dual problems. One is scientific discovery. We want to have partial differential equations and ordinary differential equations that describe plasma physics and the inner workings of our solar system and sun and our brains. That's a scientific discovery problem. The dual problem to this is an engineering design optimization problem. I want to design better artificial hearts and gas turbines and airplane wings. And that is also relies on equations that we don't have access to, things like turbulence closure models that we need to improve to do better modeling and design of things like aircraft. Okay, everyone with me? How many of you have systems where you don't have full equations to describe what you care about? Okay, good. The second challenge that we're gathered here today in this room to discuss is nonlinearity. Nonlinearity is still poorly understood. We have a comprehensive, extensive, thorough, and complete description of linear dynamical systems, x dot equals ax. We know how to solve these. The eigendecomposition is a very powerful tool for high-dimensional dynamics, linear dynamics. But nonlinear dynamics are still very much a bespoke set of problems and solutions. So maybe we have a particular solution for a special class of quadratic systems. Those do not generalize to other systems readily. So we don't have a general theory of nonlinear dynamical systems. My friend Nathan Kutz likes to point out that this is not such a bad thing. This gives us job security. So the young people in the room, you will have a job in the next 20 years because of nonlinearity. And then high dimensionality, and I think this is a little bit of an old slide. I'm actually going to modify this. It's not just high dimensionality. It is high dimensionality and our inability to measure every single aspect of that high dimensional state. So your brain is high dimensional. You have 100 billion neurons. Your neurons on average are connected to 10,000 partner neurons. So this is an astronomically large dynamical system. We have a very limited ability to measure and interrogate and collect data from that system. So systems are both high dimensional, but they also are very hard to measure. Okay? These are just some of the many challenges that we have in data-driven dynamical systems, but these are the main ones that we're going to talk about today, especially kind of the bottom two, but Koopman theory and data-driven dynamics bears on all three of these topics. If I don't have equations, if it's high dimensional and or partially sensed, and if it's fundamentally nonlinear. We want to discover a coordinate system in which our dynamics may in fact become approximately linear, because then we can do lots of things. Any questions? Good. Okay, so I'm just going to start kind of going through this. We'll see where we go in the next kind of 3 hours of my lectures today and tomorrow. So high dimensionality is probably the easiest nowadays. In the past, this used to be challenging, but now this is where machine learning really shines. It's extremely good at pulling patterns out of high dimensional data. So this is the basic idea. Patterns exist in your high dimensional data. Even very complex systems like this cloud formation past Guadalupe Island, you can look at this with your eye and you see Kármán vortex shedding. I can write down a 2 or 3 ODE system that describes this vortex shedding, even though this cloud formation and flow is beyond the ability of humans to simulate with the world's largest supercomputers. We can't simulate every scale of this system, not even close to every scale of the system. We don't understand the physics of what happens inside clouds. That's a huge open problem. But the resolution and physics required to simulate the entire system is vastly beyond our ability right now. Probably 100 years with Moore's law would be the back of the envelope guess. But we can write down a very simple differential equation to describe this because patterns exist in your data. And this is true of all data. I think this is actually one of the most remarkable properties of physical systems, and it's one of the great mysteries in the world, up there with entropy and time, is why is there so much order in our complex systems? Why do all complex systems have patterns that emerge? This means that the world lives in a low-dimensional manifold. Out of the billions of degrees of freedom, there are very strong forces creating patterns that are low-dimensional, repeatable, robust. This is true in natural systems. This is why you're able to maintain your coherence of thought right now. Maybe some of you are spacing out. I'm spacing out behind the scenes right now. But if you have a thread of your thought, that is a low-dimensional, coherent pattern living on a manifold right now in your 100 billion dimensional dynamical system. Okay? So why does that exist? We don't know, but it's very fortunate for us because that means that we can model these systems. If you're interested, how many of you are interested in fluid dynamics? Love it. Okay, perfect. These are my people. So fluid dynamics is a great example where many of these techniques have actually were born out of fluids, where we historically had equations and very partial measurements. And then we started over decades and decades and decades to get more and more extensive measurements until eventually we had full simulations of the full 3D Navier-Stokes equations and full volumetric experimental measurements. We can actually interrogate the whole system at space and time resolution, but that took many decades. And so we developed mathematical techniques to handle that increasingly large data and understand those low-dimensional patterns. So my friend Sam Tyra wrote a nice review paper about how you can find these patterns, extract these patterns, and use them for things like sparse sensing, reduced order modeling, and efficient control, which are all topics that my lab works on. So sparse sensing is an interesting one, and I think this is relevant for all of us. If a high-dimensional system has low-dimensional patterns, I don't have to measure everything in the system. I don't need to measure every single pixel in this movie to know what's happening. I can look at a little patch, or I can measure 5 or 6 points. And those 5 or 6 points, if I look at their time history, they will capitulate the main story of what's happening in this larger dynamical system. Again, patterns facilitate sparse measurements. This is how insects fly. Fun, fascinating fact, every single insect you've ever seen fly, all of them, fruit flies, dragonflies, moths, butterflies, all of them, have on the order of 10 to 100 strain-sensitive neurons on their wings. And they use those very sparse sensors to understand what the field around their wings, the fluid field, looks like, so that they don't stall their wings, so they can maintain lift, so that they can turn efficiently. They're living in a system that would require us millions of degrees of freedom to simulate. Our x dot equals f of x would have millions of equations to simulate. They only need a dozen or so sensors to pull out the important patterns in those low-dimensional flows. Okay, so patterns exist and they allow us to do efficient computation, sensing, estimation, and control. This is going to be the basis of what we do with Koopman, is find those patterns. And it's why machine learning works also. So our ability to build models from data in the current era is entirely based on the existence of patterns in our systems. So our tasks that we care about, things like modeling, optimization, sensing, estimation, and control, are facilitated with machine learning today because of the strong patterning in these systems. So if natural systems like cloud formation have low-dimensional patterns, engineered systems have even stronger low-dimensional patterns. We literally design them to be robustly patterned and low-dimensional. Good, and finally, the same optimization problems that we're trying to solve here, all of these challenges in blue involve some optimization problem. Control is an optimization problem constrained by dynamics. Sensing is an optimization problem constrained by sparsity. All of these optimization problems are challenging because the physics of the real world is nonlinear and multi-scale in space and time, which leads to high-dimensional non-convex optimization problems. How many optimization folks in the room studied some optimization? This is very important. Optimization is probably as fundamental to what we all do as linear algebra and statistics, but we almost always overlook it. We study linear algebra, we study differential equations, we study statistics. We very rarely study optimization because it's been so well commoditized. People have written such good libraries that you don't have to think about it. But increasingly, in the next 10 years, you're going to be needing to think more about your optimization algorithm. So I just want that to be in the back of your head, that that is the unsung hero of machine learning. These are optimization algorithms. Okay. Good. So patterns exist. We're going to exploit them. That's going to be the basis of half of my perspective that I'm going to give you on Koopman theory. The other half is we are trying to wrestle with nonlinearity. Nonlinearity, even very small amounts of nonlinearity, are very challenging. And so if we can find coordinate transformations that approximately linearize our system, we will have all of the powerful tools at our disposal that we normally have: eigen decompositions and prediction of any time scale, optimal control with one line of Python or MATLAB. Good? How many control theorists? I'm going to keep asking you questions until you start asking me questions. Control theorists, any control theory? I see Igor in the back. I know he's into control theory. Anyone else? Okay. I'll talk a little bit about it. How many of you have played around with dynamic mode decomposition? How many have not? Okay, everyone's heard of it probably. So I'm going to start here because this is, I think, a slightly more gentle entry point into the world of Koopman. So there is a lot of deep theory that actually came before this algorithm, starting in the 30s. And then Igor has developed a ton of this around the turn of the millennium. And then in the last 5 or 10 years, there's been another big burst of activity with Matt Colebrook and his collaborators. I'm going to start with a slightly different perspective, which is how would you approximate a high-dimensional data set as a linear differential equation using linear algebra? No fancy theory. That's the basic idea of dynamic mode decomposition. If I have a system like this fluid flow past a cylinder, if you observe this system, it looks periodic. It in fact looks like a single nonlinear oscillator to me. Okay, this is a nonlinear oscillator, but the data itself is very high dimensional. This simulation, I ran this using my friend Sam Tyra's code. This simulation required something on the order of 100,000 coupled differential equations to simulate. Okay, so that means that every snapshot of this movie in time is a 100,000 dimensional vector of numbers I need to represent the state of the system. Okay, so x1 is 100,000 numbers, x2 is 100,000 numbers. These are tall, skinny vectors. That's how I think about it. And so the idea is, can I stack my data into 2 large data matrices, X, where every column is a snapshot of my system evolving in time. The subscript here is just an index for time. And X prime, which is my data matrix, shifted 1 time step into the future. I'm just going to advance every column 1 time step in the future. So there's clearly a huge amount of overlap in these 2 matrices because all of the middle columns are the same. They're just shifted over 1. Okay? And the goal of of dynamic mode decomposition, we'll connect it back to Koopman in a minute, is to try to find the best fit linear dynamical system, xk plus 1, or x prime, equals ax. So I take my current state at time now, and I try to predict the state at the next time step by a linear evolution operator A. Pretty simple idea, right? Everyone with me so far? Good, very simple idea. And in principle, there are many ways of approaching this, but linear regression seems like by far the easiest way to approach this, okay? Now there's a few challenges. Dynamic mode decomposition was specifically born for high-dimensional dynamical systems, systems where the state dimension of x is very, very large, in the thousands, millions, or even billions of degrees of freedom. So this is like a baby example. This is our warm-up example. In fact, in the field of fluids, this is basically our pendulum. This is our nonlinear oscillator, okay? But real flows, like the flow over an insect wing or an Airbus A350 wing, might have billions of degrees of freedom with a B. And so x might be a billion-dimensional vector, which means that this A matrix, mapping a billion vector to a billion vector, right? This has 10 to the 18 elements in it. So you can't solve this easily using regression. You can't fit this on a computer. Okay, you guys see the challenge, right? Like this is too big to play around with using classical methods, even for modest size matrices. If my flow field had 1,000,000 degrees of freedom, this has 1,000,000,000,000 elements. Okay? So the idea of dynamic mode decomposition is very, very simple. Two ideas. One, this data matrix has a huge amount of redundancy because of those patterns that exist in your data we talked about. This is a single nonlinear oscillator. We know that oscillators require a sine and a cosine, 2 degrees of freedom, not 10,000, right? This is, by eye, going around in a circle. It's an oscillator. There's two numbers that probably matter. In fact, if I took a little sensor here and a little sensor here and I plotted those sensors, they'd be sine cosine pairs. And that would be all I need to characterize every other point in this data set. So the patterns exist. And the second point being, in at least high-dimensional flow field data and geophysical data and ocean and climate data and neuroscience data, and most data today in the modern world, this is a much higher dimension than the number of snapshots I have in time. I might have 1,000,000 degrees of freedom and a few hundred measurements in time. So these are tall, skinny matrices. And that means that I can approximate this A matrix, which might have trillions or more numbers. I can approximate this A matrix with a best fit low rank approximation to A. Okay, that's the basic idea of DMD. So I'll walk you through this. And so what you do is you take a singular value decomposition of x. Anybody not familiar with the singular value decomposition? So the singular value decomposition is a matrix factorization that allows you to take this tall, skinny matrix X and approximate it using an orthogonal basis set that hierarchically captures the most variance in the columns with the first entry, the next most variance with the second entry, and so on. So it's a matrix factorization that gives you a subspace, a low dimensional subspace, maybe 5 or 10 degrees of freedom, that capture 99 or 99.9% of the information in X. So even if this has 1,000,000 degrees of freedom, there's usually 5 or 10 eigenvectors that capture most of that variance in this data matrix. So you compute that SVD, that's what this X dagger is signifying, is that I compute a singular value decomposition. I project both data sets down onto that low dimensional basis set. And if you need me to, I can actually write this out on the board. We can, if you have questions, we'll just do it. And now this regression problem becomes a lot simpler and well posed in that low dimensional space. So in the high dimensional space, this is let's say 1,000,000 dimensions and 1,000,000 dimensions. This is 1,000,000,000,000 numbers. Let's say now I project it down to a 10-dimensional subspace. Does everyone understand what I mean when I say project it down to a 10-dimensional subspace? Anyone having trouble with that? This is going to be important for the next month, I think. Okay, if I project these down to the optimal 10-dimensional subspace, so now I'm in like X hat land, This is a 10 vector and a 10 vector. This is only 100 numbers. Yeah? And now I have enough data, enough snapshots to just solve for that matrix using linear regression, least squares. I do literally just a pseudo inverse and I solve for the best fit A that best maps my data in that low dimensional space forward in time. Okay? And that's the idea. And then from that low dimensional A matrix, you can compute its eigendecomposition. You can find these high dimensional eigenvectors of A that correspond to those low dimensional structures. And that's the dynamic mode decomposition in a nutshell. I totally stole this from my wife, Bing. This is her adorable cartoon of what the dynamic mode decomposition is. It is essentially morally what happens if you take the principal components in space. Sometimes we call it singular value decomposition. Sometimes we call it principal component analysis in space. And the Fourier transform in time. And it's kind of like their baby. And I didn't really tell you about the Fourier transform in time element of this. But when you take, it's a little dim right now. Let's see if I can do this. Perfect. When I take the eigendecomposition of this A matrix, so that's what the DMD is trying to do, is purely from data, I want a best fit linear operator that evolves my data, because if I have that, I can do prediction, estimation, and control essentially for free. I can't write down this A matrix because it's ginormous. And so instead what I do is I approximate its leading eigendecomposition by first projecting my data into a low dimensional subspace and solving a linear regression problem in that low dimensional subspace. So what we're getting is an approximation of the most dominant eigenvalues and eigenvectors of my A matrix. Good, okay. When you then compute the eigendecomposition of this A matrix, you get some eigenvalues and eigenvectors, right? If those eigenvalues live on the unit circle, then they're oscillating at some frequency. That's what I mean by the Fourier transform in time. So these are spatial modes. These are eigenvectors of the A matrix. An eigenvector of the A matrix has the size of a flow field of the state of my system. This is literally an eigenvector of this matrix. But this eigenvector has a corresponding eigenvalue, which means that it coherently oscillates at this frequency. Okay, so you get Fourier in time, eigendecomposition, PCA in space. That's the basic idea here. Any questions before I go on? Yes, please. Okay, so are we assuming that this is a periodic system? That's a really good question. In principle, for the algorithm, no. These can be exponentially, so this is a really good point. Thanks, Gary. The Fourier transform gives you pure tone sine waves and cosine waves with a phase. The DMD gives you a little more flexibility. It's slightly more like a Laplace transform. You can have growing or decaying real part. So you can have an exponential envelope. Like this has a slightly decaying exponential envelope. Usually your modes are a little damped or a little excited. It's actually rare that they live on the unit circle unless you have something that's purely oscillatory or unless you collect infinitely much data. If you collect infinite amounts of data, so I hope Igor talks about this, in the infinite data limit, the only thing that persists lives on the unit circle. Anything decaying has decayed and anything growing has blown up. But in the finite data limit, which is where I live as a humble engineer, you get growth and decay. Please.
Yeah, so maybe just a comment. In principle, as Steve pointed out, it's a finite dimensional approximation, but maybe it'd be slightly better to say that it's generalized harmonic analysis of linear, which doesn't require periodic rounds or anything finite periodic. I'll speak to that.
In an applied...
In the unit circle,
yeah.
when eigenvalues are the unit circle.
The recommendation I would give, at least for fluid flows, is that this is most typically useful when you have something that is semi-periodic or quasi-periodic, or at least has a dominant frequency spectrum. So I'll just play around with this board for a minute. So if your Fourier transform has peaks, DMD is probably going to be interesting. If it doesn't, it's probably going to be difficult. At least this is just a general statement for fluid flows. If I'm looking at the turbulent flow over a wing, so the flow past a cylinder I showed you, that's at low flow velocities where it's really laminar and boring. But at higher velocities, you'll start getting turbulence, which makes it much more interesting. And like an airplane wing and a fruit fly wing has turbulence. This takes that dominant frequency and it spreads it and creates harmonics and more interesting dynamics and broadband spreading. So it's a chaotic system, but with dominant frequency components. This is where DMD is going to shine, at least in that world of fluids, okay? Because you're going to be able to characterize these dominant components. So mathematically, you don't need it to be periodic, but in practice, at least in fluids, it really does help quite a lot. And I think what it does is it characterizes what you would call the kind of attractor dynamics, the quasi-periodic attractor. This is actually a great point. So this is why I want you all to ask questions, because I wouldn't have thought of talking about this until the conversation. This model is amazing at capturing the steady state dynamics. If you do this, this is an exercise for you all. You can download this data. It's on our book website. It's like really small data set. You can literally just download this. You can do this SVD. It'll have 2 modes. You project onto those SVD. You do a regression. You will get a 2x2 matrix with 2 eigenvalues, okay? Plus and minus I omega, the natural frequency of this nonlinear oscillator. The 2 modes you'll get 2 spatial modes, and then you can plot the system, okay? And it will capture 99% of the information in this system with those 2 modes. You can do this in the lunch break. It'll take you 5 minutes. If you have trouble, ask Claude, okay? This will be absolutely terrible for capturing transients. If I speed up my flow, or if I move my cylinder, if I do anything at all to perturb the system, it will be absolute dog shit, this model. It will be terrible. It will capture the steady state attractor perfectly to within machine precision. And it will capture transients not at all. Okay, this is a big point. Same thing here. It will not capture transients well at all. This is one of the fundamental limitations that we're going to learn about, hopefully, is that these systems are great at capturing kind of your steady state long-term behavior. Very challenging to bake transients into this and to capture transients, which I care a lot about because transients are where interesting engineering happens. Good.
Steve,
Yeah.
just a very brief point. It's interesting, and it's a continuation of this theme, that statement actually depends on the type of space that's underlying your computation. I'll show some examples. You have to change the functional space, and this is where mathematics comes in very nicely. If you change the functional space, you can start capturing the gradients as you.
Yeah, but this is one of the things
so
like.
in L2, that statement is correct.
Yeah, so from the engineering perspective, when you start with data and you do a linear regression, very quickly you run into some very real limitations of what you can do until you start having slightly more sophisticated perspective. Okay, history. It's important to give credit. So the dynamic mode decomposition I'm talking about was developed by Peter Schmidt circa 2009. Peter's a brilliant mathematician and engineer and basically cooked up this algorithm to handle high dimensional data. This is like a top view of a cavity flow. Does everyone picture what a cavity flow looks like? I'm gonna draw a cavity flow. I have a blackboard here. The last time I decided to do Blackboard lectures, I didn't have a single slide. This was at the Von Karman in Brussels, and I thought this will be fun. I'll just do Blackboard lectures. There was not a single blackboard or whiteboard or any surface to write on, so it was slightly a disaster. So a cavity flow, this is a really important fluid flow. This is a wall, and then you have a flow going from left to right. This creates a free shear layer, which then impinges on this wall and creates essentially these large turnovers and sometimes, crashing on the other surface. Now, cavity flows sound really esoteric until you flip it upside down, and that becomes the bomb bay doors of a bomber aircraft. And when this thing is going, Mach 0.7 or 0.8, you can get very strong acoustic oscillations at extremely high decibels, enough that it actually damages whatever you happen to be storing inside of your cavity. So a really big problem. But because of this Kelvin-Helmholtz instability and the geometry of this cavity, you get these very strong resonant frequencies. It looks a lot like this. You have a cavity frequency and its harmonics. You have the Kelvin-Helmholtz frequency and its harmonics, and then the interaction of these in this. So it's a perfect candidate for DMD and Koopman analysis. And that's where Peter Schmidt started, was essentially he took experimental measurements of a system like this, did this generalized kind of eigen decomposition in a projected SVD space, and that was the birth of this DMD algorithm that's taken over in the last 15 or 16 years. Okay. Interestingly, my advisor, Clancy Rowley, who I'm pretty sure I saw in Cambridge last night, maybe there's a lot of people who look like Clancy around here, was, I think, on sabbatical with Igor at the time at UCSB, and was sitting in the APS talk that Peter Schmidt was giving. So Peter always gets a big audience to listen to like the new thing he's doing. Clancy was in the front row taking notes, went back home to UCSB with Igor, and essentially realized that this algorithm, this linear algebra, linear regression, x prime equals ax, was an algorithm that could essentially approximate this Koopman operator he had been learning about from Igor, that Igor had been developing and talking about for the, at least decade plus, maybe 1.5 decades before that. And so this paper is kind of the bridge between these two worlds. So there's actually an earlier literature I'm not telling you about, which is Igor's literature of Koopman. I'm telling you how DMD was connected to Koopman in this famous Rowley-Mezich paper. And so they looked at this really cool flow of a jet in a cross flow. This is basically if you have a chimney in a wind, a windy chimney wind. It also has very strongly kind of quasi-periodic dynamics that you can extract with this algorithm. Okay, good. Any questions about kind of the history or the setup here? And we know, I didn't really tell you, but like I think most of you know, the whole idea of Koopman analysis is that for nonlinear dynamical systems, my next few slides will actually say what I'm saying here in words. The idea is that even for a strongly nonlinear dynamical system, x dot equals f of x, cubic, quadratic, quintic, quartic, doesn't matter, very nonlinear, there is a coordinate transformation or a lifting into a higher dimensional space where those nonlinear dynamics start to look linear. Simple statement. I'll let Igor and Matt and others, tie down the mathematics of making that statement precise. I'm an engineer. I care about when I can do this in practice. And finding that coordinate transformation where my nonlinear dynamics appear linear is, that's what I care about. Everyone, okay? And clearly the Navier-Stokes equations, this is a strongly nonlinear system. This is not a linear dynamical system. So if I can find a linear coordinate transformation that approximates this nonlinear dynamical system and allows me to predict and estimate and control using one line of MATLAB, we have taken an extremely hard task and made it a very, very simple generic task that anybody can work with. Which is essentially, I think, our job as applied mathematicians. Is to take a complex system, turn it into a simple system that any engineer can work with. Okay, so this is another set of slides I completely shamelessly stole from my wife. She makes great graphics. So this is an illustration of what the algorithm of dynamic mode decomposition does on data. So this is a data set. I want you, the audience, to describe what you see in this data set. Is it high dimensional or low dimensional?
No, it's periodic blob.
There's a periodic blob, good descriptor word. There's a periodic blob, and there's a blinking square. Periodic blob, blinking square. The data is high dimensional. I mean, 6400 is beyond my ability to picture, except unless I picture it like this, but in my mind. But the observation is low dimensional blob, blinky square. Any other bits of information here? A little bit more information. If you're going to write a summary paragraph, a descriptive paragraph, there's a couple more bits of information here.
The rates are probably not conventional. So they're probably, you probably pick different.
Yeah, maybe they're incommensurate frequencies. Blinky square is blinky a little faster than blobs.
The origin is in the center.
And the blob is in the center, good. And the
Thing looks like noise, and the square looks like stroke.
ooh, and there's noise on top of it. There's a little bit of noise on top of it. Yes, exactly. So these are the words. You could write a very tight paragraph describing this. So it is compressible. This is a compressible data set. Okay, good. What happens if I do SVD or principal components analysis? I do basic, chapter 1 analysis. It is actually low dimensional. There are 2 PCA modes. These are the 2 PCA modes that come out. It is completely mixing the 2 things that you observe. Blobby blob and blinky square are completely mixed up. That's not good. Okay, ICA, independent component analysis, actually does a much better job of separating out because these are frequency separated events. So you do actually get a blob and a square, but this is very, very noisy, okay? Dynamic mode decomposition, it projects onto the subspace. It takes this data and projects onto a 2-dimensional subspace, but then it diagonalizes that A matrix to find the eigenvalues and the eigenvectors that diagonalize that A matrix. And those eigenvectors are these guys here. And those eigenvectors have eigenvalues associated with them. This is really important. So you don't just get the eigenvectors, you also get the plus or minus I omega. So you not only get a clean representation of the kind of time-separated spatial coherent structures, you also get an estimate of their temporal patterning.
What's the difference between ICA and DMD? So what's the ICA?
It's different. I don't have time to go super deep into ICA. It basically is good at, it's kind of like PCA, but for data that is not actually orthogonal, is like the one sentence version of that is it's good for separating data where I have, and I don't think I can write out the algorithm, but if I have data like this and this, PCA is actually going to struggle. It's going to give me modes that look like that, but ICA will actually find those subspaces. So it finds the right subspaces. That's the point here, is that that's actually a really, really good point, is that this A matrix, this x prime equals AX, and let's say we're in our projected subspace, we're in our low dimensional SVD subspace, so I'm going to put a little tilde on these x's, these are little x's. This A matrix does not have to be a normal matrix for DMD to work. I can have very nearly parallel eigenvectors, which would botch PCA, but DMD is going to work much better for that. And ICA is also designed to have these like these nearly parallel eigenvectors.
One more question. Sorry.
Yes.
So the ICA is kind of got 2 nodes.
Yep.
Why is the right one noisier than the DMD mode?
That's a good question. So this has been about 10 years since we made this, to be honest. But you'll also notice that the PCA modes are much less noisy. So DMD is doing a PCA pre-filtering step before doing the eigen decomposition. So we're in a PCA filtered world here. So we filtered out all of the noise in the PCA step. ICA fundamentally is a little bit more sensitive to noise.
So you couldn't do PCA with us?
You probably can, but I don't think it's as straightforward. And you definitely don't get the frequency content out of it as well.
Pre-filtered DMD with PCA.
Yeah, so you could, but then you're trying to solve a 64,000 by 64,000, like you have to project down. You basically,
Okay.
to solve the problem, you are projecting into some low dimensional subspace. Yeah.
Just to double check, we're doing PCA and ICA on the A matrix, not on the raw data itself.
We're doing PCA on the raw data to project the, let's see, okay. Let's make this a little tilde A. So the idea is I have high dimensional X, and X prime, and there's a big A matrix that connects them. Okay, and here we're in like, you know, let's just for, you know, the sake of argument, this is a million-dimensional vector. We do principal components, so there must be an eraser in this room at some point. You see it? Cool. Lovely, thank you. Okay, so so I have my big X matrix, x1, x2 to xm minus 1. And I compute its SVD. So I say X is equal to some big U matrix times a diagonal sigma matrix times a V transpose matrix. Okay. U and V are unitary matrices. They're orthonormal columns. Sigma is a diagonal matrix of decreasing non-negative entries. The first one is more important than the second one is more important than the third one. I'm going to actually write this out. So I've got like U1, U2, dot, dot, dot. V1 transpose, V2 transpose, dot, dot, dot. And then I have, should probably be a little careful of how I write this. Sigma 1, sigma 2, dot, 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 zeros everywhere else. That's my SVD, okay? Sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma 3, and so on and so forth. What this means is that I can approximate this again, one more approximation, as sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose plus dot, dot, dot. These are a sum of rank 1 matrices. This is a matrix, this is a matrix, this is a matrix that has one independent row and column, one independent row and column, one independent row and column. And if I add those up, I approximate my X matrix. But because this is hierarchically arranged, so that sigma 1 is bigger than sigma 2, is bigger than sigma 3, is bigger than sigma 4, and these are orthonormal, I can truncate this at some point. And this is the best rank 2 approximation of X I can possibly get. Good. Where was I going with this? So that's what my SVD is. Probably should have started there. And so we usually say approximately equals UR. We pick the first R. R might be 2 or 3. Sigma R, that's the first R by R subblock. VR transpose, and we say that X is best approximated by this rank R matrix. Good, so I have my high dimensional data that lives up here in 10 to the 6th land. What I'm going to do is I'm going to project it down to this low dimensional tilde space by literally multiplying X by UR transpose. If I take U transpose, if I take this and knock it over on its side and multiply it by an X, I get 2 numbers, or R numbers in this case. And now here is where I have a tilde, and here is where I have X prime tilde, and this is an R to the R, which might be 5 numbers, or in this case, 2 numbers. Good. So, sorry, June, to your question, this was a long setup to answer your question. In DMD, we assume that our data X is in a high dimensional space where it is more measurements in space than snapshots in time, where this is a tall, skinny matrix. We assume that it has a low dimensional subspace so that there is some dominant structure in the SVD that I can use to project this down to a much lower dimensional subspace X tilde. And then I entirely work in this low dimensional subspace X tilde. So I entirely work down here. I compute the eigendecomposition of this, A tilde W equals W lambda. I compute its eigendecomposition. This is, again, R eigenvalues and R by R eigenvectors. These are the frequencies that are dominant even in this matrix. So there's a proof Jonathan too wrote down, that these eigenvalues are also eigenvalues of this big A matrix, which is cool. And that if you use these W, there's a formula to go from these W to these eigenvectors up here. So there's big A, let's call it phi equals phi big lambda. That when you go from these W, there's a formula to go from these eigenvectors to these eigenvectors. But the long story short is that we're always working in this projected subspace. Okay. And that's the projected subspace comes from the principal components. That's the UR transform space. Okay, that was a lot of detailed linear algebra. Any questions about that? How many of you have seen this before? Okay, good. Probably good to review it anyway. I haven't written this down in a while. Good. Koopman. I got 20 more minutes. I'm going to actually tell you a little bit more about the Koopman, and I'm going to try to end on a caveat. I want to get to a cautionary tale about how, at least from the engineering perspective in L2, it often doesn't work very well. So you need more sophisticated kind of mathematical analysis to make this work. Okay, so Bernard Koopman, brilliant mathematician, in 1931, when Al Capone was arrested and the classic horror film Dracula was released, wrote this brilliant paper, Hamiltonian Systems and Transformations in Hilbert Space. Essentially, this was on the heels of this revolution in quantum mechanics, which was an operator theoretic perspective. And what Bernard Koopman and several others at the time were thinking about is how to bring this operator perspective into classic deterministic geometric dynamical systems, which is what the world had been writing down for a long time before then. So I'm going to walk you through ballpark how Koopman works, again, to an engineer on a simple system where it works. Then we're going to look at the simplest systems where it doesn't work, and then we're going to try to square that circle. Okay. I realize there's a little bit of a glare in the room for some people, but this is a very, very simple nonlinear dynamical system. The first equation in x1 is linear. x1 dot equals mu x1, linear, and decoupled. Has nothing to do with x2. x2 dot, lambda times x2 minus x1 squared, is also very, very simple. Quadratic nonlinearity. I'm going to assume that lambda is a faster eigenvalue than mu, so that very quickly the system equilibrates to x squared equal x2 equals x1 squared. This is kind of what I meant by having a slow manifold, or a manifold, a low dimensional manifold in your system, is that if I start from any of these white trajectories, very quickly x2 equilibrates to equaling x1 squared, because my x2 dynamics are fast. Lambda is a big negative eigenvalue. So very quickly I shrink wrap on to this slow one-dimensional red manifold, x1 equals x2 squared. Simple dynamical system. Okay? This one will work with Koopman, this idea that there is a coordinate transformation or a lifting into a higher dimensional space where this nonlinear system will become honest to goodness linear. How many of you have seen this example before? Okay. And this is the embedding. So what we're going to do is we're going to introduce these coordinates, y1, y2, y3. y1 and y2 are just x1 and x2, no big deal. y3 is just x1 squared, the nonlinearity from my differential equation. Nothing fancy here. And you can confirm for yourself, of course, y1 dot equals mu y1, and y2 dot equals x2 dot. So it's lambda x2 minus lambda x1 squared. That's what this says. And then we compute the derivative of our y3. So notice we need to introduce this y3 to linearize the second equation, to make the second equation look linear. Now let's see what happens when we differentiate y3. Derivative of x1 squared is 2x1 x1 dot. 2x1 x1 dot is 2 mu x1 squared, which is 2 mu y3. That's honest to goodness linear. Every single term here is linear. Good. And this is the phase portrait in that three-dimensional y space. So all I've done is I've introduced a new variable y3, And now you can see these white curves here, the same exact ones here. And if you project them onto y1 and y2, it's like exactly what you see on the left. These white curves are shrink wrapping on to this slow manifold and then slowly converging to the origin. But this is a purely linear system. It's kind of cool.
So Steve, if you have the right-hand side for all the terms for polynomial variables, I guess you could do something like this with a bounded number of additional variables. Is that correct?
So that's what you would hope, but that is not, yeah, so that's actually not, this is, I cherry picked, this is the one example I could get working. There's a small family of examples like this where you can actually do this and get this kind of closure of the terms by adding in x1 squared and having that work is extremely rare. Most of the time this does not happen and you don't get closure. There is no bounded polynomial representation that you can truncate and have it
When the
close.
right-hand side is polynomial.
Even when the right-hand side is polynomial. It's a very special subclass where that does work. And an interesting subclass to characterize, actually. There's some interesting algebra there. But this is a case where it does work. And even further, you could compute the eigenvectors and eigenvalues of this K matrix, this 3 by 3, and diagonalize it and pull out the leading eigenvector, and that would correspond to an eigenfunction. Yeah, an eigenvector of this matrix has an x1 and x2 and an x1 squared, so you can add those up and get an eigenfunction. And so my two eigenfunctions are the eigenfunction corresponding to eigenvalue mu is just x1, and the eigenfunction corresponding to eigenvalue lambda is x2 minus bx1 squared. Or b is just a number that pops out of this math, out of the time scale separation, how fast or slow these variables are.
What's the purple thing? Is that related to one of the eigenfunctions?
Goodness, that is the. Good question. Again, it's been about 10 years since I made this. This blue manifold, it's a really good question. So this blue manifold here, good. When I introduce this third variable y3 equals x1 squared, I immediately enter the possibility of having non-physical trajectories. Any trajectory of this system that started from an actual x1, x2 naught at time 0, this initial condition y3 naught has to be x1 naught squared.
Oh,
So this is the x1 naught squared initial condition manifold. If I start anything off of this blue is like non-physical. So this is an embedding, but everything physical in that space has to be on this blue manifold. And that's kind of illustrating that the cut of this blue manifold and the projection down is where everything interesting lives.
Green.
I couldn't tell you what the green is. The green has to do with this B vector. But the red and the blue are the ones that really matter. This is my slow manifold. This is the physical initial condition manifold. And the intersection and projection is where the interesting dynamics happen.
And then Marco's question is presumably about these manifolds intersect.
Yeah, exactly. So the structure of this original dynamical system gives you some indication of when this will or will not work.
Just,
Please, yes.
just a small comment because it relates to the earlier question. In this case, you can actually write two equations, right, for two eigenfunctions.
Or the two eigenfunctions.
And you're going to have a two-dimensional linear system. So exactly the same dimension as the original space, and then keep the whole physics. It relates to what I'm going to say later today, but it's not by, as Steve correctly pointed out, it's not by just expanding the space of polynomials. It's actually a true transformation on the original space. And then there is a theorem that tells you very precisely when you can do that or not. I'll mention it in my lecture.
We'll get to a counterexample immediately. Question from June.
So you can describe a system perfectly with two eigenfunctions. So it's like the lower dimensional description is 2 dimension, but then the actual linearizable equation is 3 dimension. So it's the
No, so this is important. I'm trying to illustrate this idea. So the original Koopman idea is not necessarily talking about eigenfunctions. The original idea is that if I take my x dot equals f of x and I lift it to an infinite dimensional Hilbert space, not even a 3-dimensional space, just an infinite dimensional Hilbert space, it becomes linear in that Hilbert space. if I can find eigenfunctions of that linear operator in Hilbert space, they do become functions in my original function space that I can work with, eigenfunctions. So this is just playing around with first lifting to somewhere where it becomes linear, and then finding the eigenfunctions in this lifted space. So we don't always have to do that. If you can just write down the eigenfunction, more power to you. That's better. Like the eigenfunctions are what we care about. We often lift to find them and then project onto the eigenfunction space. Again, that's what DMD is doing. That's the whole Koopman DMD perspective, is that if I measure 1 million flow variables, I'm already in this like lifted high dimensional state. And so from that super duper high dimensional state, I'm trying to find my low dimensional eigenfunctions, so I'm already in a lifted state in the DMD world. That's kind of why I'm illustrating here that just adding a variable lifting does often linearize your system. Then you can find your eigenfunctions and project back down to a minimal kind of core eigenfunction subspace.
But isn't there a third eigenfunction?
There are harmonics of these, just like 2 mu is also an eigenvalue, and 3 mu and 4 mu and 5 mu, like all of those will be also, and mu plus lambda, mu plus 2 lambda, there's this whole integer lattice of eigenvalues and eigenfunctions, but these are what you would call the principal eigenfunctions of the system. Open question from I'm sure that the mathematicians know this, but I don't know a priori how to tell how many principal eigenfunctions I will have in a system. I'm guessing, again, if I have something that's a single nonlinear oscillator with one frequency peak, there will be, one eigenfunction. If I have multiple frequency peaks, I'll have multiple principal eigenfunctions, but I don't know how to formalize that mathematically. I'm sure they do.
Yeah, if the spectrum in the particular space you're working in is point spectrum,
Yep.
and your underlying system is n-dimensional, then they're exactly n.
Okay, cool, thanks. Okay, so again, why do I want this representation instead of that representation? I can simulate both of them. They're both, computationally amenable. The short answer for me is that I want to do optimal control, okay, or design, or whatever. Like I want to do estimation and control, and it's much, much easier to do for linear systems, right? Like we know linear quadratic regulator is a one-line command in Python. It has a closed form-ish, it's a solution of the Riccati equation. It's simple. So let's say we take the same dynamical system as before. I've written it in a slightly different form. And I add a control input plus 0 mu in the second channel. So I can modify the x2 dynamics. I can push on the system in x2. And now I write down my Koopman augmented linear system. So this is an honest to goodness x dot equals ax plus bu linear control system. So I can plug this in to the LQR command in Python and get an optimal controller. How many of you have done LQR and linear control? Okay. When you do an optimal control, you get an optimal gain matrix that multiplies this state. And so my optimal control has a K1, K2, and K3. These are just numbers that weight those terms. But notice that because my state in this Koopman land is technically a nonlinear function of x1, my controller, my optimal linear controller, has a little nonlinear element. This is quite nice. I'm actually getting like an optimal nonlinear controller. You can prove that this is optimal nonlinear control. This is just the LQR cost function. So that's nice. You can do this optimal control and you get a nonlinear controller, which is presumably better. The straw man, the baseline, is to just linearize about the fixed point. That's what we would do classically. I would do a simple linearization at the fixed point. And I would use that 2x2 linearization and do LQR. And I would only get a 2x2 linear controller. That's my baseline. That's my baseline in white, is a simple linearization. In red is my Koopman linearization, where I get a little bit of extra information. And you don't need to, these are just the trajectories. This is the cost function. This is my objective function I'm trying to minimize using simple naive linearization and Koopman optimal nonlinearization. So you get about 3 times better control performance when you know the structure of that nonlinearity and you find this linear optimal embedding. That's a big deal. That means 3 times less fuel burnt to get to the origin. This is like if you're trying to navigate a ship in the ocean and you just try to go from point A to point B, you're going to be fighting currents the whole time. If you know the structure of those currents, you can hitch a ride and do something a lot more energy efficient, a lot more optimal, even faster in a lot of cases. Okay, that's the whole point here. So that's the promise. Now, where does it break down? I've got 7 minutes to tell you where this breaks. Let's try an even simpler system. X dot equals x squared. Polynomial dynamical system. Let's try to embed it. Let's see if this works. Okay. X dot equals x squared. We're going to try the exact same trick as before. We are going to add a state, which is the nonlinearity. We need to add an x squared state so that we can linearize the y1 equation. What happens when I differentiate y2? Derivative of x squared is 2xx dot. 2x times x squared is x cubed. So y2 dot is x cubed. That's not in the span of x and x squared. So I need to add an x cubed. What's the derivative of x cubed? 3x squared x dot. That's 3x to the fourth. That's not in the span of x squared or x cubed. So I need to add an x to the fourth. And I need to go on and on and on. So I keep adding terms, and you get this fancy structure here where it never, ever, ever closes. I need all of the polynomials to add. So this is kind of the rub, is that like the theory is really for infinite dimensional Hilbert spaces. It's not for, you know, any old arbitrary finite dimensional representation you pick. In fact, any old finite dimensional representation you pick is with high probability not going to be a good one. Okay, so finding those is going to be very, very important. Now you can get some approximation like this. If I increase the order of my approximation, I do get better and better for some time horizon. It can be useful, but there's a fundamental limitation here. Everyone see the problem? Okay. There's a really beautiful. Yeah, okay, so this is an important one. Yeah, this you can't talk about this ODE at the airport. Because it blows up in finite time. There is some time at which this blows up. And so we don't talk about it, but yeah, like this one is not a well-defined function. Now what you can do, and I played around with this, and I remember I asked my then at the time advisor Clancy Rowley about this, and he literally like scratched his head and wrote down the solution. He wrote down the eigenfunction. He wrote down this eigenfunction. This is an eigenfunction of the system. You can just jot this down, very simply confirm that this will in fact solve x dot equals x squared. Now I know in retrospect now that 100% he had already solved this, and because this is the simplest one you would write down and play around with. And it's actually a really elegant and very instructive form of solution that you can play around with yourself. So here's how you solve this. What you do, I'm sure most of you have looked at asymptotic analysis and have done some asymptotics, like you derived Bessel's functions and Airy's functions for nonlinear ODEs. So you can do the exact same thing here. You take a two-sided Taylor series expansion for x, a Laurent series, right? So you have positive powers of t and negative powers of t with coefficients. And you plug it into both sides of this equation. You assume that there is some, phi. Let me say this, I botched it. Assume that your phi has a two-sided series expansion, a Laurent series. So positive powers of x and negative powers of x. And you plug this into that equation, and you assume that phi dot equals lambda phi. You can basically derive a recursion relationship for all of those coefficients in that two-sided series expansion. And when you solve for them, you'll get e to the minus 1 over x as the only expansion that is reasonable. Okay, so you can play around with this. And this is actually a very reasonable solution approach. You can write down something called a Koopman PDE. I'm sure that my mathematical colleagues will tell you about this. But you can basically write down a partial differential equation that has to be satisfied for any Koopman eigenfunction. It's a really nasty PDE. And if my ODE has 3 state dimensions, I get a 3-dimensional nonlinear PDE. If I have 10 state dimensions, I get a 10-dimensional nonlinear PDE. So it, in some sense, is harder than solving the original problem. But this does satisfy a partial differential equation that you can write down for any ordinary differential equation. I have 2 minutes, so I'm going to end on one final note, and then I'll pick up in the afternoon a little bit more. If I naively pick a basis, polynomials is probably the worst basis you can pick for many reasons for most problems. But let's just say, you know, I pick polynomial. I'm lazy. And you truncate it. Let's say I truncate it at y3. So I get this little block 0, 1, 0, 0, 0, 2, 0, 0, 0. I get this little 3 by 3 subblock, but there's all of this stuff to the right-hand side. You get something very interesting. You get an aliasing effect. So how many of you know about aliasing in the Fourier transform? We've all seen this before, right? Like I erased my Fourier transform picture, but if I have, my Fourier transform, let's say I measure at this frequency. Everything here is going to get reflected over and contaminate my signal. Aliasing. We know about aliasing. There is a direct analog of aliasing in Hilbert space that happens here. If I truncate this system here, all of this stuff aliases and contaminates all of these eigenfunctions and all of these eigenvalues. That is the simple way of saying it. There's a much more mathematically precise way of saying it, but these basically, anytime you pick a bad truncation in a bad basis, you are contaminating your entire spectrum and you're aliasing all of those higher order effects that you're truncating. It's just like this aliasing, but in this Hilbert space. And that's a huge, huge problem. And that's one of the problems that Matt has spent a lot of time addressing, is basically how do you find better coordinates and better bases and better eigenfunctions that actually work. So 10 years ago, when we were playing around with this and trying to figure out how to make this work, we ran into a lot of early walls where things did not work well in practice. In the last 5 years, there have been a lot of advances that have made this a lot more robust and a lot easier to find these eigenfunctions reliably for real systems of interest. But you have to be aware of things like aliasing and truncation issues, and when there actually is only an infinite representation, and so on and so forth.
For this example, when you truncate, the eigenvalues are just 0, right?
Yeah.
How
Which
does
is
that interact
problematic.
with the sort of the physical?
That's a really good question. I mean, my gut feeling is that it's because this is a Jordan block, and so you're getting these secular terms, is I think probably something, I don't know. That's a great question. I don't have a good answer for that.
So if you truncate it and then have this weighted shift and then try to control with.
That's a really good question. I haven't thought about that. Yeah, because you get like basically 0 eigenvalues on any truncation. Yeah, I'm not sure why the approximation gets better and better and better with more truncation in this case. This is an example where this is a bad basis. Like I would not play around with this basis. I would not try to rationalize what it means in this. It's just a bad basis. Like it's not the right basis to represent this system. Fundamentally, right? Like positive powers of x don't give me e to the minus 1 over x. Like I need negative powers of x.
Also the dynamics, as you said, it blows up. So
It blows up in finite time. Yeah, so this coordinate transformation, if you map it, it actually stretches out that blow up into infinite time, which is also an important property of this. That's why you need those negative
I think
times.
it's just generally hard, right?
Yeah.
You're complaining it doesn't work, but it's kind of a hard system.
Well, yeah, but I mean, I want to apply this to all kinds of systems where I don't know the answer, where I don't know the dynamics, where it does have, exotic, I want it to be robust, and I want it to be generic. Again, the job of us applied and some pure mathematicians is to take hard problems and find ways of systematically making them easier so that engineers can, use them more generically. And this is currently at this point that I have stopped at, this is not a generically useful tool. The next several lectures, you will learn more how to make this a generically useful tool. But I want you to 10 years ago, there was a lot of promise. There's a lot we could do if we could linearize systems, but there are these walls where it's, at this point, not a generically useful tool. So we're going to learn about how to make it more generically useful.
With the control, you might want to control it to not blow up.
Ideally, yeah, you might want to control it to the origin. Yeah. I mean, I would argue that this is not probably the right way to control the system, but yep. Okay, good. I'm going to stop here, and I will give another extension of this in the afternoon, and then I'll give a final lecture on Tuesday morning, which is tomorrow morning. I'll be here. Okay, thanks, everybody.